Hello everyone, welcome back to my YouTube channel. In this particular video, we'll be looking into full fine-tuning hands-on. So basically we are going to develop code from scratch for full fine-tuning. Now we are going to fine-tune a large language model, which is GPT-2 here, onto a dataset that we have created. Now I have created a simple dataset from LLM. So basically I'll be giving you the dataset link in the description box. You can simply download it from there and have it in your if you are doing practice side by side, then you can use that. So now over here I'm using Kaggle. Now why Kaggle? Because Kaggle provide free GPUs so that we can simply train our model without any hassle. So that is why I'm using Kaggle. Also onto Kaggle, we have to make sure while creating a notebook, we need to make sure that certain things has to be there while creating the session. So if you start the session, before that you need to simply keep your accelerator as GPU T4 into 2. That means 2 GPUs you will be getting for this particular if you select this particular parameter. Next, you have to select language as Python, because everything we are going to develop, that will be in Python only. The persistence has to be files only, and you can simply write the environment as always use the latest environment, because uh, this will simply avoid any issues. Also make sure that your internet is always on over here, and you need to make sure that the under the tags you have this GPU option. That's it. Once you do that, you can simply start the session. Now my session is already started. You can see over here my session has got started, and I have currently a CPU and 2 GPUs in here. Currently they are not in use, so now we'll be using it. Before starting on to the code, we'll be first seeing the dataset that we are having. So now this is a full fine-tuning example. Basically we are going to update all the weights of the GPT-2 model such that it will be trained to work according to the new dataset protocols that were defined. So over here under the datasets, I have simply created this particular dataset over here. You can see we have a sheet over here, that means an Excel file in which there are 4,000 rows and 3 columns. So let me show you the kind of dataset that we have in here. So basically it's a simple Excel dataset. Over here we have 3 columns: title, language and topic. As an input we'll be giving title. That title is nothing but sort of a sentence which contains certain language, that is the programming language, or it also contains the topic. Now this topic basically depicts what is being discussed in this particular sentence. So let's talk about the very first one: vectorize operation instead of iter rows in pandas. Now here, by looking at the sentence, if anyone has any knowledge about Python pandas, so you can simply understand that the language that we are talking about is Python, because in Python we have pandas, and the topic that we are discussing over here is nothing but the pandas. So you can just relate it like NER, that is name entity recognition, or topic entity or topic recognition from whatever you have as an input. Similarly, if I would like to show you some other example, like for example you can see this ESL int event handling slow query 2021. So basically this thing ESL int is the topic that we are discussing in here, so this comes under the topic, and this specifically is present in JavaScript language. So that is why the language, under the language we have JavaScript as the output. So this is a labeled dataset we can talk about. It's a kind of supervised full fine-tuning technique. Here we have such 4,000 examples, and we are going to train the GPT-2 model on all these examples. We are not going to use any kind of PEFT technique over here, because this is full fine-tuning technique. So also you need to make sure that this full fine-tuning technique will also take huge computational resources, but since our model that we are taking here, that is GPT-2 itself, is small, so there is no worry about huge computational resources usage. So now I hope you have got an overview of the project, what we are going to do in here. Now since we have gotten ample information about the project, let's dive into the code now. So we have initialized a Kaggle notebook. Whenever you initialize a Kaggle notebook, you will get this particular piece of code by default. So this code will make sure whatever datasets are present in your dataset folder, it will be simply giving you the path of it. So I'll simply execute this, and you can see we have got one single path in here. It says that my Excel file that I'm going to use is present at this particular location. Next, for installation purposes, we'll be using four libraries: uh, datasets, accelerate, evaluate, and transformers. I have added bits and bytes and peft over here, but we are not going to use it. So you can simply install all of them, and this will take certain amount of time. But once you do that, you will be, uh, you know, uh, till the end of the session, it will remain in your notebook. Next is the part of importing certain libraries that we are going to use in this particular project. So let's go one by one. So we are using NumPy pandas for data pre-processing of our Excel file, that is the dataset. Next, we are going to use Torch for playing with the GPUs. Next, we are going to use the datasets. Now, this particular library specifically we are using for loading and pre-processing the dataset easily. So I'll show you how we can use it. We are also importing transformers. So under the transformers, we have used auto tokenizer, auto model for causal LM, trainer, and training arguments. So basically, we have imported auto tokenizer for loading the tokenizer model which we are going to use for GPT-2. So this auto tokenizer will simply load the correct tokenizer for your model, whatever you define. Next, we have also imported auto model for causal LM. Now, specifically, we are using this because this entire project is all about generation of JSON. So basically, once you give an input as a single simple string, you will be getting a JSON as an output. So you are simply predicting something, you are generating something. That is why we have used auto model for causal LM. So this causal LM is nothing but the decoder only model, wherein we have to predict certain new tokens, new set of tokens. So that is why we have used this. This will simply load a causal language model like GPT. Okay, so I hope you understand this. Next, we have imported trainer and training arguments. This imports are specifically used for high level API for training the models for with like minimal boilerplates. So I hope the significance of all this is clear to you all. Now we have simply defined, or we have fixed certain randomness over here. So we will be using seed as 42. That means every time we are going to load dataset or whatever maybe we are using, it will be having a fixed random set. That means whatever batches are going to be created, it will be fixed all the time whenever we run it newly. So I hope this is clear. So next, we have also used the torch model. CUDA dot is available, which will simply specify whether CUDA is available. That means GPUs are available onto our system. If it is, then it will print CUDA, otherwise it will print CPUs. So I'll simply execute this, and after taking some time, it will simply import the libraries and will print what type of device we have onto our system, whether it is CUDA or CPU. Ideally, if you simply select this GPU, you will get CUDA as the output. So let it run. Let's move on to the next cell. So this particular cell is totally specific to loading your dataset and pre-processing it. Pre-processing in the sense they're simply going to give a final touch to the dataset so that once it is prepared, we can simply use it for training purpose. So I already told you our goal. Our goal is to make this particular dataset that we have. Let me show you that again. So LLM will get this input, single string, and in the output it will give a JSON. Now JSON will have two keys, language and topic. Each key will have a value. For language it will be Python, for topic it will be pandas. So a JSON will have to create. I hope you understand what we are going to do here, but still I'll simply walk you through the code. So basically we have defined the path of the data that we have. We have already got this in here. I simply have copied and pasted it over here. Next, we'll be defining the title column, that is the input variable, and the label column, which will be the output variable, on which will be present in our dataset. So my older dataset that we have, uh, that contain three columns. Now my new dataset that I'm going to create, a pandas data frame, it will contain two columns, title and category. Category we can simply Title we can simply put it as it is, and category, for creation of category, we'll have to simply pre-process the two columns out of the older data frame into a category, that is the JSON. So for that, we are simply going to first load the data frame, for which I have written a function load data frame, which will simply import, which will simply load the Excel file pd.read Excel. And there is some exception handling over here. Then once the data frame has got loaded, we'll simply apply this particular technique of converting it into JSON. So what it will do is, it will simply using the lambda function, it will simply iterate over each row. It is having three things: title, language, and topic. Once it come across a language or a topic, it will simply make a JSON out of it. That is the language, which is the row of language, which will be the value of that particular row, and the topic will be the value of that particular topic row. So it will create a JSON and it will store it, it will append it in a list. So likewise it will do that, and it will create a data frame which will contain two things: title column and label column. So title column will contain list of strings, and the label column will contain list of JSONs. So over here you can see I have defined a simple function which will simply convert each set of JSON string that we have already created above. It will simply convert it into a compact JSON. So it also handle the cases where input label is already a dict or a JSON string or anything else. It will simply raise an exception out of it. And then we have simply print the head of the data frame. So over here you can see we have this particular data frame wherein the first column is title, it is containing a string, and the second column is category, it is containing a JSON, a pure JSON without any error into it. So once we have created it for like around 4,000 rows, that is the all the number of rows that we have present that were present in the earlier data set, we are ready with our data. Now it's time for splitting our data. So now always remember, for full fine tuning technique or for any type of fine tuning technique, we have to split our data set into train and test set. To be very specific, it has to be train and validation set. Splitting criteria is basically a hyperparameter tuning kind of thing, wherein you have to define what percentage of data you have to put into train set and what percentage of data you have to put into the validation set. Ideally it is 80-20, but as per your experience or as per the data that you have, you can simply uh, you know you can simply fluctuate it. So I'm here keeping the percentage of the training data as 90%, and the remaining data, that is 10 percentage of data, will be used for validation purpose. So I hope this thing is clear over here. Here we have simply used the dataset library, from which we have simply converted that pandas data frame, from which we have simply sampled it and created two different sets of training and validation. Let me tell you this specifically what we are doing. So in the first line, we have simply used the sample function. What we are doing here is we are simply shuffling all the values. Fraction equals to 1 simply means that we are simply taking a sample which will contain all the rows from the original data frame. Now why we are taking all the rows? Because we just have to simply shuffle it. And here we have defined random state as seed, which we already have defined above as 42. That means every time we'll refresh this, we'll rerun this, we'll get the same set of values. So over here you can clearly see now this will shuffle the data frame and keeping the same variable df. Once that is done, we'll simply split our data into train set and test set with the threshold of zero point 0.9. That means training will contain 90% of the data and testing will contain, that means validation will contain 10% of data. Next we have defined two variables, that is df train and df val. Here df train will contain the 90% of data, and val will contain the 10% of data. uh, and then we have simply printed the size of the data. So obviously out of 4,000 rows, 90% comprises of 3600 values and 10% comprise of 400 values. So we are now done with this. Next step is to load our language model that we are using. So here loading the language model is super simple, because in the transformer library everything has been done readily. You just have to put the model name and the loading will be done. Can just mention the model name properly. Over here we are using GPT-2. The output directory we are mentioning over here, that means whatever fine-tuned model we are going to create, it will be present in this particular directory after execution or after saving purpose. After saving the model, it will be stored here. Next we are going to simply load our tokenizer. I already told you that whenever you are dealing with fine tuning, you have to load the model as well as you have to load the tokenizer of that particular model. So for tokenizer loading, you have to use auto tokenizer from pre-trained. In that, you just have to pass the model name, and I have set the padding as left. Now why we have set this? Because here we are working with causal language model. We are going to deal with token generation. That is why we have kept the padding side as left, because we want here that the padding token should be added at the left instead of to the right, because it keeps the latest token aligned at the end of the sequence. So I hope this thing is clear to you all. Now next we are going to simply create our special tokens. So for padding purposes, we are GPT model doesn't have a readily their token for padding thing. So we are going to simply ingest a new token, that is pad. This is how you can simply create the token, and we'll name it as pad token. So here under the add special tokens, we can simply define it so that the tokenizer will be now aware of this particular token also. Along with that, we are also going to add this particular token JSON underscore end. Now why we are going to add this particular special token? Because in the output we are going to create a JSON. Now a large language model will always try to generate the tokens unless it gets the EOS token, that means the end of the sequence token. But here in case of JSON, if we want strict JSON as an output, then in that case we might not get EOS after creating the JSON, after the JSON is being created as an output. So for that purpose, we have to like introduce a JSON underscore end token, which will tell the large language model whenever a JSON underscore end token appears. That means the JSON has got created and you just need to stop there. Now this is not exactly equal to the EOS, because EOS is where the large language model by itself generates that token, because the entire semantics of the sentence has got completed. But here JSON underscore end will forcefully tell the language model to stop generating, even if it isn't, even if it has not completed the entire sentence. But since it has completed the JSON, it will simply stop here. I hope this significance is clear of this particular token. Next, we'll simply load our language model. So we will do that with the help of auto model for causal LM from pre-trained, and we just have to give the model name. Once you do all these things, you will simply get your model loaded. Now we also want the language model to be loaded onto our device, that is CUDA, that means GPU. So for that we'll simply write model dot to. We are transferring our model to GPU. Let's just run this, and you can see the loading has got done, and it will now save the model onto the GPU. I hope this particular cell is clear to you all. Now let's move on to the next cell, wherein we have defined our token limits and prompt templates. Also we are going to also we are going to do some pre-processing on top of what we have done earlier on the dataset. So here we have defined two things, that is the source length and the target length. Now whenever you talk about a large language model, every large language model will have a source length, a maximum input length, and a maximum output length, which technically we call it as a context window. So now over here, whenever you talk about a larger context window, so in that case you need to have higher computation, you need to have you need to do a larger pre-processing, a larger amount of training onto your dataset. But here we are going to deal with a simple dataset. That is why I have simply put the input token as 128. That means 128 tokens I can put as maximum in the input, and output I'll be getting 32 tokens maximum from the language model. I won't be getting more than that. Next we'll be defining the prompt template. So every single language model has its own prompt template. If you know about Llama or Mistral, it has its own set of tokens that has to be defined in the prompt template, such that the language model understands what is being done now, what has to be done next. So likewise I have created title colon, here comes the title. Next, there is a slash n, that is a new line, and then the JSON part start. That means the language model will understand that once that here is the title, and now with the help of this particular title, it has to generate a JSON. So this is how it works. Once we define this prompt template, we have to just pass it through entire dataset that we have created. So I have created a simple function over here, build example, which will take in the two columns, title and the target JSON. That is nothing but the category. It will simply create a prompt out of it by simply passing it in this particular prompt template, and it will create two variables, prompt and target. Prompt is nothing but which contains the title along with this string. Target will simply contain a JSON. This particular token, additional token, wherein the language model will understand this has to be the limit to create the entire generation sequence. It will stop once this token appear. Now, once we do this, we'll simply have to create IDs of these two strings. Now, always remember, a language model will not understand a string as an input. It will always understand a number as an input. So, we'll always have to create IDs, tokens, or I would say tokenized version of your tokens using the tokenizer module. So, we'll simply use this, and that is why we have loaded tokenizer explicitly. In this, you have to give the prompt, you have to set the truncation equals to true, so that this ensures that the sequence doesn't exceeds the maximum length that we have already defined over here. Next, we have also used this add special tokens, which will simply assign it to false, because we control special tokens manually over here. We don't rely on the EOS, we are simply relying on JSON underscore end and all those stuffs. So I hope this thing is clear. We'll be getting the tokenized version of your prompt and target variables, which will be called as prompt IDs and token, I mean the target IDs. Once we do that, we'll simply jot it down. That means we'll simply concatenate these two and we'll call it as a simple input IDs. Next, we have defined this variable labels, which will simply tell the model which token to be predicted next. -100 over here signifies masking out the prompt tokens such that loss is not computed for them. Next, we'll also define the attention mask over here for each entities. One here represent of real tokens. That means no padding used yet. So after this, it will simply return a JSON which will contain input IDs, which will contain labels, which will also contain attention mask. These three things are very important for training purpose. Once this is done, we'll simply pre-process the entire batch, the entire data batch wise. So over here you can see, while calling these two functions, we have simply used the map function, into which we are calling it batch by batch. By simply keeping batched equals to true, first we are calling the pre-process batched function for the train set, and then for the validation set we are doing that. Under the pre-process batch, it will simply take the batch and it will simply pass it on to the build example function, which will create this particular JSON for each and every entity, and then it will store it as a unique list. You can see we have three lists: input IDs, labels and attentions, which will contain attention mask. And finally we'll be getting this a single JSON which will contain list of each entity. So I hope this thing is clear to you all. Let's execute this particular cell. You can see the mapping has been done successfully. Now next we'll talk about the data collator. Now we'll see what is a data collator, why we need to use this. So basically I'll just answer your question, why do we need a data collator. So basically, after pre-processing step that we have earlier that we have done earlier, each example will have three things: input ID, label and attention mask. It can have different length. Yes, every single entity is not of the same length, right? So it will have different length, but training will always and always require a uniform tensor shape. So it requires a fixed length, a uniform length of shape. That is why we need to use the padding sequences in this particular scenario. Now Hugging Face has built-in collators, that is the data collator for language model, but here we need custom left padding. That is why we have defined this particular class of data data collator for causal LM left padding. So here in this we simply have defined tokenizer, which will give us the pad token ID, you can see here. And then we have defined the label pad token. This will simply take the value as -100, because like it's a standard ID in PyTorch or Hugging Face, which is ignored by loss calculation, so that padding doesn't contribute to loss. So I hope you are getting some idea about it. Next, we have defined this left pad function, which will simply pad the tokens on the left side of the sequence. You can simply see the logic is very simple. It will simply put all the padding values to the left of the sequence wherever it feels that the sequence is not equal to the maximum length of sequence that it has. So I hope uh, this thing is clear. Now alternatively, you can also use right padding, but here in our case, since we are using causal LM, we are not going to use it. We are going to use left padding. Now this call method that we have defined over here, it will simply do three things. It will first find out the longest sequence from the entire batch through the max length. It will find out that, and then for each feature in that particular example, or I would say batch, it will simply pad the input IDs with tokenizers pad token IDs. Then it will pad the labels with -100, so loss ignores padding, and then we'll pad the attention mask also with 0, so attention ignores the padding positions. So I hope these three things are clear to you all. And then finally we'll return the padded output, the input IDs, the labels, and then the uh, attention mask. And this is how the collator over here works. We'll do it for the entire tokenizer set. So now that we have defined the object of data collator, now we'll use it. Before that, we'll also define certain functions. Over here you can see there are a long list of functions that we have defined. So here we have defined certain list of functions. Now over here, this particular functions will be helpful for us to like generate a nice custom compute matrix, which will be used for evaluation. It will also handle the causal LM outputs, JSON extraction, and the schema normalization all in one. So now we'll dive into every single function one by one. So the very first function over here is sanitize IDs. Now this will simply ensure all the token IDs that are present, they are valid. If anything negative or out of range tokens are found out, they will be replaced with the padding tokens. That means the padding IDs. So this sanitize IDs will make sure about it. Next, we have this particular extract first JSON function, which will take in string as an input. Now, basically, what will it do is it will simply look for first balanced set, or I would say a block in a string. So, as you know, as in the output, we have a JSON string. After that, we have a JSON end token that we will be getting at the end of the string. So, once it addresses the JSON end token, it will stop if something special token like this is found. If there is no valid JSON object present, then it will simply return this particular empty string as an output. Next, we'll use this particular function, minify the JSON string. Now what is this used for is that it will simply load a JSON and normalize that JSON to a fixed schema. Like for example, there will be only a language and a topic key present inside that particular object of JSON. Otherwise, it will simply remove that irrelevant keys or any kind of white spaces or ordering issues which are present. It will remove that particular row. This will make sure that there will be a compact, hassle-free, and issues-free JSON. Next, we have defined this particular compute matrix function, which is very important and very crucial in this particular case. So this particular function will handle both things, like for example passing the prediction labels or evaluation of the predictions object. So here in this particular function, if the model return logits, it will logit means a particular value for every single next token that is going to be generated. It will take the argmax along with the vocabulary dimension to get the token IDs. So this will ensure this particular thing. If already the IDs are present from the custom trainer, then it will simply use them. Then it will simply like whatever functions we have defined above, the sanitize IDs and the minify JSON, it will simply apply all those functions here, and it will do the respective work about it. It will decode the target text, and then it will simply count for the exact match. It will count it as exact match if there is an exact match for the prediction as well as for the input label. and it will simply return the valid JSON about on top of it, which will be a fraction of samples where the model produced valid JSON. Now, why this functionality is good? This particular function that we have defined, it is good because it handles both the logics and the token IDs. It also makes the evaluation schema robust. Also, it guards against the invalid outputs by using the try except block. Also, it like gives two clear metrics, that is the exact match you can see over here and the valid JSON. So this will ensure a proper sanitized flow. Let's execute this, and we have done defining the functions. Now the next is that we are going to define a class which is generative trainer. This will be the main class which will taking the trainer object as an input. This will basically be the main class wherein we'll be passing on all the arguments, model, dataset, everything will be passing on. So what this does is it basically first inherits the trainer class that is already defined in the transformers library. It overrides the prediction step function. We have simply used this particular thing to override some new logic on top of it. Now it will simply control how predictions are produced during evaluation and validation purpose. So here what we are doing is it will simply call the original trainer prediction step with prediction loss only equals to true. So we have explicitly mentioned this particular entity over here. We have set it to true. That way we'll always get the correct loss calculation, which is important for reporting the evaluation loss. Also, it makes sure that if the caller only wants loss, we'll skip this generation and return loss, none, and none, like this. This tuple will be uh, returning. Next, we have defined the gen model, which will simply make sure that if we are training on multiple GPUs with torch.nn.data parallel, your model is wrapped inside the dot module over here. You can see we are ensuring this particular thing. Next, we have defined the generated tokens. Now, what it will do is it will simply take in the input IDs. You can see over here. Then it will take in the attention mask that we produced earlier. It will take the max new tokens. We have set it to 40. Then we'll simply set the do sample as false because already we have done sampling earlier. Then we'll do some definitions of US tokens and PAT tokens, which we already have defined earlier. And then finally it returns the loss, the generated tokens object, and the input labels. That's it. This is the significance of this particular class. This particular custom trainer ensures evaluation compares true generation against the labels. So I hope this particular class definition is clear to you all. Now let's execute this. Next is the main and crucial step while before training your model. So for this we'll have to like define two things. First is we'll have to call the generative trainer class that we have defined and overwritten. We also have overridden the prediction step inside it with our custom logic. We'll call it and we'll pass on certain things, but into this there is something called as a argument section. Now this argument section is nothing but it will take a training argument class object which will contain some hyperparameters. Now these hyperparameters will be responsible for efficient training. The more you know about the dataset, the more you will understand about the hyperparameters, and the more you trial and test, you will get better results accordingly. That is why we have defined this particular args variable, which will be a object of the training arguments from the transformers library. It takes the output directory which we already have defined, wherein the the output model, that means the fine-tuned model, will be stored. We also have defined the per device train batch size. So basically each GPU or CPU processes 8 samples per step. If you define larger batch size, then it will lead to faster convergence. If your GPU memory allows, then you can simply use it. Otherwise you can simply lessen it down to 4 or 2 also as per your GPU specifications. Next we have the per device evaluation batch. We have set it to 8. It will ensure the batch size for validation. Usually you can set it equal to the training batch size, but can be slightly larger since no gradients are stored. Next, we also have to define the learning rate. I have simply defined it to 5e minus 5, which is very small, so that our model gradually learns everything and it doesn't overfit. Also have made sure that it doesn't underfits. Here we have specifically used the Adam WF learning rate. So it is typical for transformer based fine tuning. Uh, Lower if you can keep it lower if the training is unstable, or you can keep it higher if it is underfitting. Next, we'll keep the number of training epochs as 3. You can simply increase or decrease it as per your language model as well as dataset. So it ensures that the number of passes over the datasets will be 3. Then the evaluation strategy will be epoch. You can simply keep it steps, or you can simply keep it no. You can have the save strategy as epochs only. Then which means after every epoch it will save the model checkpoints. Then there are certain parameters like save total limit. I've set it to 2, so that it will keep only 2 checkpoints, which will simply avoid the disk bloat. Next, we have this logging steps, which we have kept it to 50, which will basically log the training loss every 50 steps. Whenever 50 steps are completed, it will log the training loss. If it is smaller, then more frequent logging, but it will be slower. Next, we will report to none. Next, we have this load best model at end. Will set it to true. It will make sure that after training it reloads the checkpoint with the best evaluation metrics. Next, we have the metric for best model, that is the exact match that we have defined earlier, which will ensure that it will choose the best checkpoint based on the exact JSON match rate. Next, greater is better is set to true, which signifies the higher metric equals the better model, which is true for accuracy metrics. Uh, if you're optimizing the loss, then you can simply set it to false. Next, we have used this remove unused columns. We have set it to false because it will simply prevent the trainer from auto dropping dataset columns. Next is the FP16. We have set it to torch.cuda.is available, wherein we'll be getting the device availability, that is the GPU. It will enable the mixed precision training, that is the float 16. If the GPU supports it, you can simply set it to this particular thing. This will speed up the training, it will reduce the memory usage. If you're specifically using CPU over here, then it will be totally ignored. So I hope the significance of every single argument that we have defined over here as an hyperparameter is clear to you all. You can simply explore this in detail, in depth. If there is a huge demand, then I will simply create a separate video on these training arguments, where I'll explain each of them in detail with examples. So if you want it, just write it in the comment section. Next, we have simply used this particular object generative trainer. Here we have to simply put everything that we have done till now. First is the model. Wherever we have loaded the model, we'll simply pass it on here. Next, the arguments that we have discussed earlier, this training arguments, will simply pass it on here. Okay. Next, the training dataset, wherein we have all the things, that is the attention mask, the input IDs, and all those stuffs. We'll pass it here. Then the evaluation dataset, that is nothing but the validation dataset that we have created. Next is the tokenizer model that we have for the GPT-2. We'll simply pass it on over here. Next, the data collator, which we have defined explicitly as a class. Next is the compute metric. Uh, we already have defined the function of compute matrix, which will compute it based on the exact match. And this is how we get our trainer object ready. Once this execute, we can simply get our trainer object. Now to train your model on top of the dataset train and val, you can simply use trainer.train. And once the trainer.train executes, that means your training is done. After that, you can simply use trainer.evaluate, which will evaluate your model performance. So I hope this particular thing is clear. Now I'll simply execute this particular cell. Let's execute it and the training will start. So this will take certain amount of time based on the complexity of the language model you are using, also based on the complexity of dataset that you have. So you can see after around like 4 to 5 minutes the training has got completed, and you can see we have got 3 epochs. For each epoch we have got the validation loss reducing. It was first zero point zero 0.06, then it came to zero point zero 0.02, and then it came to zero point zero 0.01. That means our model is not overfitted. So now you can see the final list of parameters that we have over here. Now once our model has got trained as well as evaluated, now we will simply now we'll simply define a function which will be used for the testing or the prediction purpose. Whenever a new entity or a sample comes, how our model performs on top of it. Let's see. For that I have defined this particular predict underscore json function. Now what it does is it will simply take title as an input, which will be in the form of string. It will take the max new tokens, which is by default 40. It will take the sampling as a boolean value. It will be false or true. Ideally it is set to false. It will also take the temperature, which is a floating value which ranges from 0 to 2 or 0 to 1 in some cases. So if it is high, that means if it is closer to 1, that means your model will hallucinate. That means your model will generate some variations in your output. And if it is closer to 0, that means your model will simply generate precise output. Then we'll also have a top p parameter in the list of arguments, which is by default zero point 0.9. It will be only used if sampling is enabled. It will simply restrict the top cumulative probability mass. Now, inside this particular function, what we have done is we have simply taken the title and we have passed it on to the prompt template that we already have defined earlier, which contain title colon the title, your title, whatever title you have defined, then a slash n and then a JSON. Then we have used this tokenizer object into which we have defined the prompt. Here we are simply tokenizing the prompt that we have created. Next, we'll be setting this particular arguments, max new tokens and all those things. If sampling is set to true, then it will simply enable the random sampling and also enable the temperature and top p to control the diversity. If it is set to nothing, it means it is default as false. So basically it's a greedy decoding kind of thing. Now once the generation is done, we'll simply use the decoder. We'll simply decode the tokens to our original English words or original natural language words. Also here it ensures that wherever it finds the JSON underscore end token coming appearing there, it will simply cut the rest of the part and it adds the JSON underscore end marker back if found, so that by the end of the execution of this particular function you will get a strict JSON object. No less or no extra tokens will be outputted. Now let's try to check whether it is working clearly. Here I have used this particular simple sentence. I want to do machine learning. Let's execute this and let's see what output we get. So you can clearly see it has outputted a JSON object, or I would say a JSON string, which has strictly two keys: language and topic. Language is Python, topic is machine learning. I hope you are understanding the power of this particular thing that we have developed over here. We have made it to output only a strict JSON always, because it's a full fine tuning technique and there are lesser chances that it will hallucinate. Also, now let's try to add on a few more examples over here. You can see I have inputted a different sequence over here. What is a decorator in Python? It simply creates this particular JSON. Instead of answering the question whatever I have asked, it strictly creates this particular JSON without any extra token or a less token. This JSON is pure strict JSON, wherein it has identified the topic that we are discussing is decorators, and the language that we are discussing in here is Python, which is explicitly mentioned itself inside the query. Even if you do not mention certain things inside the query, it will still work to some extent. So I hope you are understanding this powerful thing that we have developed. I know language model wise it is smaller language model that we have used. Also dataset wise we have used a very baby dataset, kind of a very basic baby dataset. But The motive of this particular video was to make all your concepts clear related to full fine tuning technique. It is very difficult for anyone who step very new to this particular field. It's very difficult for them to understand, to collect the data, to learn these types of topics like fine tuning or so in gen AI. My motive was to make you aware about this. Now I hope you might have got or developed at least some confidence in you that you can do fine tuning irrespective of the language model or irrespective of the dataset that you get, specifically the full fine tuning part. In the upcoming videos, we'll be also looking into the PEFT techniques that we have discussed in the previous video, if you remember, the introductory video to fine tuning. Let's move on to the further thing. Here we just have like saved the model onto a directory. You can see if I would show you this particular Kaggle working inside this, the model might have got saved. Yes, you can see this particular checkpoints and the fine-tuned model has got saved, so that in future if you want to use the same model, you won't have to again train it from scratch. You can simply use it from here. I have just shown you that from the stored model that we have like stored here in this particular output directory, how we can get the generations. So you can see I have simply used this particular libraries again. I have defined the model path here. This time I have defined the fine-tuned model path that we have saved. Now I have loaded the tokenizer as well as the model of this particular fine-tuned model, and have simply given the query and certain simple instructions like what will be the max length and all those things, EOS token and PAT tokens. So after generating it and decoding it with the help of the tokenizer, we'll be getting the same output. You can see, let me just simply execute this. Clearly you can see we have got the generation as title, what is Python, JSON, colon this particular thing. Now why we are getting these things, title and JSON? Because this was defined in the prompt template, and earlier here inside the predict JSON function we had done this particular pre-processing. If you see this, we had done this pre-processing, so that we'll only get this particular JSON and not the entire prompt template. Here also you can simply put certain functionalities of cutting out the earlier part and simply get a JSON as output. So I hope this thing is clear. And this brings us to the end of the video. I hope you enjoyed this particular video a lot. I know I might be fast in this particular video because there were a lot of concepts that has to be covered in this particular video, but I tried my level best to cover everything in this one short video. I hope the intricate, difficult concepts are also now clear to you all. My motive has got achieved, and I hope you like this particular entire video. And if you want to, come across more such videos, if you want to get more informative things about fine tuning, then you can simply subscribe to my channel. Stay tuned for it. You can also bring your suggestions and feedbacks on this particular video in the comment section. I'll be happy to go through it. For more such videos, do like, share, and subscribe to my channel. Also hit the bell icon and don't forget to follow me on Instagram. Please join me on Telegram. Thanks for watching. Have a good day ahead.